Very happy evening to all participants and today's speaker, Dr. S. Vedraj sir, Assistant Professor, NIT Tiruchi. Now, I request Dr. N.V. Edwin Paul sir, Professor and Head of the Department of Mechanical Engineering, to deliver the welcome address.
Thank you, Dr. Dilevan sir.
Thank you, sir.
Good evening, everyone, and very warm welcome to all. I hope you all had a fruitful and engaging discussion yesterday. And we are now ready to enter day 2 of this exciting faculty development program. As we continue our journey of learning, growth, and professional enrichment, we are truly honored to welcome today's distinguished speaker, Dr. S. Vedraj sir from NIT Tiruchirappalli. We are delighted to have you all here for this important and insightful discussion on harnessing solar and wind power for electrolytic hydrogen generation. Very special and esteemed welcome to our expert for the day. Thank you for being with us, sir. It is my distinct pleasure to formally introduce our distinguished speaker. Dr. S. Vedraj sir has been serving as an assistant professor in the Department of Mechanical Engineering at NIT Tiruchirappalli since 2018. He is an accomplished engine researcher with over 15 years of global research experience. During his PhD at the National University of Singapore, he worked extensively on projects involving the adoption of alternative fuels for CA engine operation using innovative engine modification techniques. Following his doctoral studies, he pursued postdoctoral research at the Clean Combustion Research Center, King Abdullah University of Science and Technology. There he worked with both metal and optical engine setups and collaborated closely with Saudi Aramco on the FuelCom 2 project. His contribution to developing methods for detecting and suppressing super knock conditions in downsized engines lead to a granted US patent, a remarkable achievement. Dr. S. Vedraj sir holds deep expertise in several advanced high-efficiency combustion modes such as homogeneous charge compression ignition, partially pre-mixed combustion, and pre-chamber spark ignition. He has successfully tested these modes under wide and challenging engine operating conditions. He has an impressive research record, having published 42 journal papers in reputed high impact journals, contributed to 2 book chapters, and secured 1 US patent. After joining NIT Trichy, he received a major research project under the SERB ECRA scheme worth of rupees 43 lakhs. This project enabled the establishment of the state-of-the-art flame and spray visualization research laboratory at NIT Trichy. Additionally, he serves as the coordinator of the Center for Combustion and Emission Studies at NIT Trichy, where he leads foundational research on combustion and emission formation relevant to various industrial applications. His expertise spans engine testing, test bed optimization for high efficiency combustion modes, combustion and spray visualization, and the adoption of low and zero carbon fuels for engine applications. So, ladies and gentlemen, with great respect and enthusiasm, please join me in extending a very warm welcome to Dr. S. Vedraj sir. Welcome you, sir. Sir, unmute. Please unmute, sir. Mohan sir, please enable.
Yeah, can I? It's audible now?
Yeah, welcome, sir.
Yeah, thanks for the nice introduction, sir.
Thank you, sir. Thank you.
Happy to see you all. So let me share the screen and I'll just start with the things. Right. So things are visible?
Oh, yes, sir. Visible, sir.
Fine. Right. Shall I start now or?
Yes, sir. Yes,
Okay.
Sir. Please continue, sir.
Thanks, sir. And if there is any technical glitch or you're not able to see the slide movement or audio issues, you just let me know.
Okay, sir.
Right. Thanks. So good evening to one and all. Right. So
Good evening,
today I've been given a topic on harnessing solar and wind power for electrolytic hydrogen generations. And for this wonderful online faculty development program on green hydrogen and advanced storage technologies for sustainable carbon-free future. And as Sir has introduced about me, I've been an engine researcher for past 15 years, right? And the recent times, for the last 5 or 6 years, I've been started working on hydrogen fuels, right? So hydrogen combustion systems we are developing. And in the last 1 or 2 years, I'm also getting into hydrogen generation because the world is moving towards hydrogen technologies and the hydrogen economy. So the basic outline of my today's presentation. So first we'll start with the background, right? So what is the status of renewable energy sector in India? And I'll also walk you through the current facts or the government schemes that have been introduced to promote the renewable energy. And what are the setbacks of renewable energy systems and how hydrogen can bridge that setbacks. I'll just go through in the background section. And then we'll see about the general aspects of hydrogens and the different color codes adopted for hydrogen systems. And the hydrogen production methodologies. We'll have a broader perspective of hydrogen production methodologies. And specifically, I'll try to focus on the electrolysis and the different types of electrolytic systems. And next, we'll see how this renewable energy systems can be harnessed for hydrogen generation, basically adopting electrolytic hydrogen generation mechanism and the economic considerations. So, and what are the emerging technologies that are in current research that will foster hydrogen production. That will also I'll touch. And finally, how it is being used in end applications. Hydrogen used in different ways. As my expertise is with combustion, I will just give you a brief about how hydrogen can be adopted for different engine concepts. And majorly, herein I work with pre-chamber systems. So, what do you meant by pre-chamber system and how it can be incorporated? So, I'll give a brief about that, and finally with the concluding remarks. So, recent times, there is a rapid increase in the electricity demand, and majorly due to the population growth as well as the rapid industrializations. And if we just look into the statistical data from the Ministry of Power, in the last decade, right? So in the March 2014, the total electricity generation installed capacity is only about 250 gigawatts. Now it is almost doubled, right? So the way towards is there'll be a huge demand for all these industrialization and all the sophisticated instruments and other things that we are procuring. Everything relies on electricity, and government are pushing towards, they are not interested towards starting up with the conventional thermal power plants or coal power plant systems. And what are the major things that comes up with the renewable sector? So government is pushing towards renewable energy and to combat the climate change. And according to October 2024 statistics, we have crossed to 200 gigawatts of renewable energy capacity in India. And government has made a clear promise that it will go on with achieving 500 gigawatts of energy in the year 2030. And if you look back into the renewable energy capacity in India, major contributors are the solar, wind, and hydro. And biopower and small hydro is of very small percentages. And solar power contributes nearly about 45% of the total renewable energy capacity. And wind is the second one, which contributes nearly to 23.5% of the total renewable energy capacity. So as I said, India targets for 500 gigawatts of electricity from exclusively from renewable energy by 2030. That's the target they have set. And if we individually look into the developments of solar and wind, last decade is a drastic or rapid development with both these sectors. And the statistics shows these things. In the year 2014, the total solar energy capacity that is being installed is roughly about less than 10 gigawatts. Now we are about 110 gigawatts, right? So which means it's kind of a 11-fold increase. And we are India. As India, we are geographically favorable for solar energy extractions, and we lie in the Tropic of Cancer, and mostly 300 days out of the 365 days in the year we get solar energy. And government has taken initiatives to push the solar energy systems to greater heights. And when it comes to wind energy system, it is slowly increasing the capacity of the wind. And compared to 2014 and 24, the total amount of wind energy system capacity is almost doubled, right? And similar to solar, we also have a very larger coastal lines, and because of the larger coastal lines, there are the wind energy accumulation is higher, and it is kind of a favorable situation for extracting the renewable wind energy systems. And majorly, people focus on either the coastal regions near to Tamil Nadu, or majorly on Gujarat, where the wind velocity or the wind energy availability is higher. And recent times, government has taken several initiatives to promote both the solar as well as wind energy sectors. So I'll just brief you about the different schemes that has been developed in the recent times. So first is PM Surya Gar, the Prime Minister has introduced in the year 2024 with a vision of enabling rooftop solar installation for nearly 1 crore households. And it provides subsidy for installing the solar installation, as well as it provides 300 units of free electricity on the monthly basis. And within a year time, I think they have achieved nearly 10 lakh installations, and it has been in the news article in the recent times. And this one is a very huge step by the Indian government. So they have planned to introduce solar park scheme. So with the established capacity of nearly 40 gigawatt of solar energy by 2026, and they have planned to go with 53 different parks across 13 different states. And currently nearly 14 gigawatts is already operational. And Rajasthan Badla solar park is the largest one, and it has a capacity of about 2.25 gigawatts in a single place, where it spreads like in a large area. And second is floating solar projects. So instead of occupying the land areas, government has provided incentives to promote floating solar panels on the water bodies. And one of the Asia's largest floating solar park is opened in Omkareshwar, Madhya Pradesh, with a capacity of about 600 megawatt. The major idea behind it is saves land and the area that it requires to install a huge solar park can be laid on the floating system, so that the water evaporation issues can also be avoided. And next is PM Kushum. This is majorly meant for agricultural farmers, wherein they provide subsidy of about 30 to 50% for developing solar pumps. And they also allow the excess energy that is being developed is to sell it back to the electricity suppliers. And second one is kind of agrivoltaics, so wherein they integrate the solar panel with the farming. So you have farming below, and you try to have solar panels on the top, so that the area is effectively utilized. So they tried for 105 kilowatt system in Jodhpur as well. The final one is a viability gap funding scheme. This is the only scheme that has been introduced to promote offshore wind energy projects. We all know that offshore wind energy is quite costlier when compared to onshore wind energy projects. And the government wants to explore the capacity of wind available in the offshore conditions. And they plan for the implementation of 1 gigawatt of capacity. 500 megawatt is planned in Tamil Nadu coastal regions, and 500 megawatt of installation is planned in the shores of Gujarat as well. So we have been through this solar and wind energy system for a quite long time. And I just want to summarize what is the key advantages and limitations of the systems, and how hydrogen can bridge this limitations. So we all know that when we talk about solar and wind, it is abundantly available, and it is inexhaustible, renewable in nature, clean energy. And when it comes to the operating cost, it is lower, because once you install these solar plants or the wind farms, it kind of have a lifespan of nearly 25 to 30 years, and maintenance cost is also quite low. And that is one of the advantage. And second thing is you can scale it to different levels. So you can have a very miniature systems, as well as you can have a very large wind farms, as well as solar systems, right? So they go with rooftop installation, as well as they have a very large parks. And nowadays with wind energy also, they have generated this windless turbines, and they have started installing in the highway to extract the wind energy. So it is kind of flexible. You can go with either the small scale system or a large scale system. And we all know that the environmental impact it creates is very minimal. So no air pollutions, no water is being involved. So it's kind of advantageous. And one major thing is it provides energy security, right? So in the year 2022, when Russia-Ukraine war started, the scenario is Russia stopped its natural gas supply to European nations. And there was a huge demand for natural gas at that time. And European nations, they felt the necessity of energy security by that time. So from now, that period onward, every country is keen on developing the energy security policy so that they want to have their own energy resources. And India also is keen on these schemes. And next is technological advancements. So if you consider the solar energy, what has been developed a decade ago, now the cost involved in the development of solar panels or installation is reduced by nearly 90%, right? So from 2015 to 2025, if you compare, the cost is reduced by 90%, and majorly because of the automations and advancement in the technologies and all these things. So we all know these positive aspects. So when it comes to limitations, we know solar and wind is not available throughout the year. And whenever it's available, we have to utilize it. So these kind of energy system is kind of intermittent energy. And if you take in a particular day also, you'll have variable energy generation. It's not like uniform energy generations. And this provides a drawback, like if you install the solar or wind systems in directly with the grids, then the grid integration and stability comes into play. So it is like it disturbs the grid scenario. So you have to, even though we are capable of developing a higher power output, considering the grid stability and integrations, they reduce the solar plant installation capacity or wind installation capacity. And next is about the energy storage challenges. And energy storage challenges is if we are having a small scale solar or wind energy systems, then we can adopt batteries and we can store the energy that is being intermittently produced and we can use it for continuous operations. But when we go with large scale development of solar parks or wind farms, the capacity of the batteries is also a major concern, and the cost involved in developing these kind of batteries is also a major concern. And the most important thing is when we talk about solar and wind, the initial cost is quite higher and it takes longer payback period as well. And it also has geographical limitations. But when we talk about India, we don't have that point. So we are well equipped with both the solar as well as wind energy systems. So now how these limitations of solar and wind energy can be addressed with hydrogen technologies. So one is with, we have talked about the intermittent nature of the solar and wind. So instead of using a battery pack to store the produced energy, we can go on with using that renewable energy to produce hydrogen, and it will try to produce hydrogen whenever we have excess renewable energy. So during the high solar or high wind output, and whenever the generation is low, the hydrogen can be utilized in kind of any applications like fuel cells or other systems, so that you provide back the energy. So you store it whenever it is high production and give it back whenever you have low generations. And energy storage limitation is you can store hydrogen as gas, compressed gas, or you can liquefy hydrogen as well. And it provides a long-term energy storage solutions. And the batteries have a limited capacity and it's kind of suited for short-term storage. But with the hydrogen, you can go on with the long-term storage solution as well. And grid stability, hydrogen, as I said, it stores the energy during the higher output and it provides back whenever the generation is low. So it just tries to smoothen out the fluctuations in the renewable energy operations. And The last one is decarbonization of hard to electrify sectors. So certain sectors like the industries, heavy industries, where people try to use furnaces, right? So where they require very high temperature to melt the metals, and for the reactions, chemical reactions to happen, they need to have some kind of furnaces where the heat is being generated. In that scenarios, it's difficult to electrify things. You can't use electrical heating mechanism, and it will not be much efficient as well. And in that scenarios, if you are able to convert this renewable energy into hydrogen, and that hydrogen can be combusted and it can provide the required heat energy to process these industries like steel, cement, and chemical industries. So these are the ways where hydrogen can come into play. And this will give you the overall picture of what we intend to talk today, right? So when we talk about solar, we have two different ways of extracting the energy from the solar. One is with the solar PV cells, right? So we use PV cells and extract the solar energy and produce electricity. So the electricity that is produced from your solar cell is a kind of DC electricity, direct current. And when we go with the solar concentrated solar power, wherein we try to extract the heat energy from the sun and targets it towards a receiver, and where you get higher temperatures, and you allow some kind of organic cycle, Rankine cycle to follow, where you use some liquids to absorb this heat, and it gets vaporized, and then it expands in a turbine, and that turbine is linked to a generator to generate your electricity. So the electricity that is being generated here is kind of AC electricity. Similarly, when we use wind power, so here we have given a representation of horizontal axis wind turbine, so you can go with vertical axis as well. And all this wind turbines is meant to produce alternating current. So you need to have a converter to convert all this AC to DC and provide it to your DC bus. And this DC current can be used in an electrolyzer to produce hydrogen. And that hydrogen finds application in a number of scenarios like fuel cell, heating application, transportations. You can generate synthetic fuels and industries and so on. And in recent times, you can see the number of publications on hydrogen production from solar, wind, or the hybrid system has increased a lot, right? So the statistics says that it follows an exponential trend in it denotes like the people interest towards having renewable energy for hydrogen generations. So the general aspects of hydrogen. So hydrogen is kind of the most abundant element in universe, and it's if you take sun, you have majorly hydrogen and helium. And but when we talk about Earth, it never exists in its molecular form of H2 compound, right? Rather, it exists as a compound form with other elements like hydrocarbons or ammonia. All these things, it exists in nature, but hydrogen as a pure one, it doesn't exist in Earth. And it's an invisible, colorless, and odorless gas. It has the highest energy density on the mass basis, whereas when you go with the volume basis, it is the lowest energy density, right? And it has a unique characteristics. It can be stored as a gas, compressed gas, and it can be stored as a liquid, or it can also be stored in certain application as solid metal hydrides, right? So this unique characteristics makes it ideal for energy carrier scenarios. And when we talk about hydrogen, nearly 95% of the hydrogen that is produced till date is by majorly by steam methane reforming process. And the trend of electrolysis due to the higher cost that is involved, it's slowly taking up. But majority or nearly 95% of the hydrogen that is produced is from steam methane reforming process. So in the World Economic Forum in the year 2017, they mentioned about using renewable energy for hydrogen generations uh, to replace whatever the hydrogen that is produced by steam methane reforming process, so that it will boost the hydrogen economy. So we want green energy to take forward. And based upon that, Iceland has committed to become the world's first hydrogen economy by 2050. Hydrogen economy means it relies only on hydrogen for all its energy needs, right? And the major reason is Iceland is a place where you have higher geothermal energy. So using water and dissociating it and developing hydrogen from the geothermal source is quite feasible. And that's why they have went with this treaty. And India, it's currently the cost of hydrogen production in India is roughly around $3 to $4 per kg, and they want to slash it down to $1 per kg by 2030. And India started the green hydrogen mission, so wherein the government has set an ambitious target of achieving a green hydrogen production of nearly 5 million metric tons, that too by 2030. So it's kind of a huge target, and many companies have started working towards that, and we'll see what the scenario of hydrogen production in India as well. Right? I think most of you have heard about the different color codes of hydrogen, right? So when we go with the traditional process, so we classify that as gray, black, and brown. So gray is whenever we use the well-known steam methane reforming process, and we don't capture any emissions, right? So that's kind of a gray hydrogen. Black hydrogen is we use gasification, coal gasification by using anthracite coal. So if you use lignite or brown coal, then it's called as brown hydrogen. So these are the traditional methods for producing hydrogen. And now people have come up with different colors, right? So blue hydrogen is about the same things, that is steam methane reforming process. And one difference is you try to capture the carbon emission that is coming out of this steam methane reforming process and sequester it and use it for different applications. So then it is called as blue hydrogen. Whenever you try to extract the emissions, capture the emissions and store it for different usage, then it is called as blue hydrogen. Then it is Turkish hydrogen is kind of dissociating the methane molecule into hydrogen and solid carbon, so that nothing is left out into the atmosphere as gases. So you can use solid carbon and use it for different processes. And red hydrogen and pink hydrogen is red is kind of thermolysis process wherein we try to use water and take it to very high temperature levels and split it into hydrogen and oxygen. So majorly they use nuclear heat to dissociate the water to produce hydrogen. And pink hydrogen is you adopt electrolysis process, whereas the electricity is produced by nuclear energy. So that is pink hydrogen. And purple hydrogen is a combination of these two, right? So red and pink combination is known as your purple hydrogen. So the red, purple, and pink is related with the nuclear energy. So green hydrogen, the topic of today. So will be majorly from the renewable energy sources, and wherein we try to electrolyze the water without emitting any CO2 emissions. Yellow hydrogen is majorly when you use only solar power to produce hydrogen through electrolysis process, then it is called as your yellow hydrogen. Gold hydrogen is whenever we have abandoned oil wells, we use some kind of microbes or enzymatic process to produce hydrogen. That is gold hydrogen. White is whatever we get from the geological reservoirs. Along with the natural gas, we get some hydrogen as well. So that's called as white hydrogen. And there are different methodologies that they adopt for hydrogen productions, right? Various feedstocks. You have algae. They grow the algae, and the algae absorb the sunlight, and it produces it. Whenever the sunlight hits on the chlorophyll content of the algae, it excites the electron, and that electrons helps in photolytically breaking the water molecules, So that is one method. Second method is you go with dark fermentation. You can cultivate the algae and you allow that into hydrolysis process, and the glucose that is being formed is being dissociated in the absence of oxygen to produce some acids and hydrogen as well, right? So that's how algae contributes. Wood, coal, oil, and alcohols, they can be used in either the reforming process or the gasification process, wherein they try to disintegrate the larger hydrocarbons to form syngas and majorly extract hydrogen out of it. And the unique one is your water electrolysis, right? So which we'll deal in detail in the today's lecture. And different processes, they categorize it with electrochemical process and thermochemical process and photochemical process. So we have different resources. So majorly when it comes to electrochemical electrolysis process, we use water as a feedstock, and we take electricity either from non-renewables or renewable resources and dissociate the water compounds. And there are different thermochemical process wherein we try to provide the thermal energy and dissociate it to form hydrogen. Either we use natural gas, coal, liquid fuels, biomass, carbonaceous material, and so on. And the photochemical is kind of use the photo radiations, solar radiations, and the light source may excite the electrons and it dissociate the water particles as well. So majorly when we talk about green hydrogen, so water splitting is the one of the major things. So you have three different scenarios: thermolysis, photolysis, and electrolysis. Thermolysis, as I said, you heat it up to very high temperature levels and break it down to simpler compounds. So water electrolysis usually happens, water thermolysis usually happens at a temperature of more than 2500 degrees centigrade. And you can also go for hydrocarbon thermolysis. So kind of methane cracking, wherein we produce turquoise hydrogen. So the temperature is roughly around 1000 to 1200 degrees centigrade. Photolysis is kind of a chemical, the photons from the sun energy is being used to split the water. So you have two different scenarios. One is photochemical or photoelectrochemical. So you can adopt both to dissociate the water compounds. And main thing is electrolysis. We use electric current to split the water into hydrogen and oxygen. There are four different types, and alkaline water electrolyzer is the most well-known one. And proton exchange membrane is also known technology wherein we can generate hydrogen with higher purity. And a solid oxide electrolyzer as well as anion exchange membrane electrolyzer is kind of evolving technology, right? Anion exchange is kind of evolving technology, and solid oxide is also have recent times there is a number of scenarios where they try to use steam instead of water to electrolyze it to form hydrogen as well. We'll see the working of individual things in the coming slides. So first is alkaline water electrolyzers. So majorly it's used concentrated alkaline electrolyte. Either they go with potassium hydroxide or sodium hydroxide, roughly about 5 m of that in the water. Roughly 30 or 40% of this is into your water solutions. And the anode as well as the cathode material is separated by a diaphragm. So the diaphragm will allow the OH hydroxyl ions to flow, whereas it prevents the gas that is being generated in the anode as well as cathode. So it doesn't allow the gas mixing. Whenever DC electricity is applied to this electrolyzer, so the cathode water reacts to produce your hydrogen gas, and it also produces your hydroxyl ions. This hydroxyl ions is transported through the membrane diaphragm, and it reaches the anode. At the anode, this OH ions, which has excess electrons, it liberates the excess electrons and it produces the water and the oxygen gas. So this technology is mature and it's a low cost hydrogen generation technology, and it has a longer lifetime. And the catalyst that is being employed in this alkaline water electrolyzer is kind of a non-precious metals. The major problem with this alkaline water electrolyzer is its slow response time. And so because of its slow response time, it is not ideal for the fluctuating nature of renewable power. And next is the proton exchange membrane electrolyzer. So here you have a proton conducting polymer membrane between the two electrodes, which is a kind of solid, non-porous, and it allows only the protons to pass, protons in the sense hydrogen ions to pass through. So whenever you apply the currents, water molecules are oxidized to O2 in the anode, and the hydrogen ions, the protons that is being formed in the anode, flow through the polymer membrane, and it reaches the cathode. So wherein it takes the electrons to form the hydrogen gas. Right, hydrogen gas is produced in the cathode side, and oxygen is produced in your anode side. And key features here with proton exchange membrane, you get high purity hydrogen. So it's almost 99.99% pure hydrogen can be obtained with PEM electrolyzers. And it also offers higher efficiency, and it provides faster response. And the major problem is it involves the platinum group of catalyst for the cathode and iridium group of elements in the anode, which increases the cost. And the membrane that they use, the proton polymer membrane, is also costlier, which increases the cost of the system. And also it takes up only fresh water, right? It's a kind of pure water. You should not have any impurities, should be desalinated, and you have to use only clean or pure water. So that's one other disadvantage with PM electrolyzer. So next is anion exchange membrane electrolyzer. So it combines the advantage of both the alkaline, so that is combining the cheap catalyst with the PM, that is polymer proton exchange membrane electrolyzer systems. And here the anion exchange membrane that we use in between the cathode and anode allows only the OH ions to be transported from the cathode to anode, and it doesn't allow the gases that is being formed to flow through as well, similar to other things, right? And here the water is reduced to hydrogen in the cathode, and it produces hydroxyl ions. That hydroxyl ions flows through the membrane to the anode. And in the anode, the hydroxyl ions undergo oxidation to generate the free electrons as well as the oxygen. And here we can use low cost material as like the AWE, right? Alkaline water electrolyzers, and thus it can be cheaper than proton exchange membrane. And here also we use the electrolytes. Unlike the alkaline water electrolyzer, here we use only low electrolyte concentration, for example, 1 m of KOH in the water. And so that it doesn't create the base doesn't create any kind of erosions in the cell. And this kind of technology is still under development, and people have tried using this anion exchange membrane electrolyzer for electrolyzing the saline water as well. It's kind of a research scenarios. And the final one is the solid oxide electrolyzer. As I mentioned, here people use only steam instead of water. Right, so it operates at a very high temperature, roughly about 700 to 900 degrees centigrades, and it's split the steam into hydrogen and oxygen. So whenever you apply DC electricity, so at the cathode, the steam gains the electrons, and it split into hydrogen and oxide ions. So these oxide ions will pass through a ceramic layer, electrolytes, and towards the anode. And in the anode, the oxide ions releases the electrons and forms oxygen gas. So it provides higher electrical efficiency because most of the energy comes as a heat, and we try to maintain the temperature at the higher. And we use expensive material and high temperatures because the temperature involved is around 700 to 900 degrees centigrade, which means you have to provide some durable materials, which is quite expensive. Now, when we talk about the advancements in the electrolyzer development, so when it comes to alkaline water electrolyzers, so research focuses on developing advanced catalysts for both the anode as well as cathode to reduce the over potential as well as enhance the reaction kinetics so that it improves for higher efficiency. And researchers are also exploring for alternative catalyst material that are abundantly available and are cost effective and have lower environmental impact. When it comes to PEM technology, PEM water electrolyzer majorly relies on expensive noble metals like platinum or iridium for the hydrogen evolution reaction and the oxygen evolution reactions. So extensive research has been carried out in for the past 2 or 3 decades to reduce the noble metal loading and substitute with more cost-effective alternates like nickel ions or cobalt ion alloys, and go with the transition metal oxide as well. And people have started working on with bifunctional catalysts, which improve the system efficiency by catalyzing both the hydrogen evolution reaction as well as the oxygen evolution reactions. And coming to the harnessing of renewable energy for hydrogen generations. So it's like, as we discussed earlier, right? So when we use the concentrated solar power to generate heat, people use some organic cycles to take the heat and expand it in a turbine, and turbine is connected to a generator and it generates the electricity required for the electrolyzer. So we generate this electricity and provide it to the electrolyzer, and it can produce the green hydrogen. So this is how it works with the concentrated solar power or the solar tower that we intend to develop. And second is with directly from solar PVs, right? So solar PVs generates the electricity and it's used for hydrogen generations. And here people try to make sure that they have a power conditioning unit with maximum power point tracking system. So the intent of having the maximum power point tracking is whenever we have solar and wind energies, due to the environmental conditions, the load that is being implied is vary, right? So they vary the voltage as well as the current, so that at the given environmental conditions and loading scenarios, the curve, the load versus power curve will ensure that it is existing at the maximum power extraction point. And the overall PV electrolysis system efficiency is approximately 10%. And final one is your photoelectrochemical. So in addition to the supplying of electric current to convert your water into or dissociate your water into hydrogen and oxygen, the sunlight is also exposed to your electrodes, and whatever the photons that we that is being received from the sunlight excites the electrons in the electrode material, and it aids or it assists the reaction process to dissociate water. So it's kind of whenever the photon strikes, it creates a photoexcited charge carriers to generate generate green hydrogen. So wind-based, when we talk about wind-based, we have two different scenarios. One is onshore and another one is offshore. So you install the wind farms and try to generate the electricity. And as I said, wind, you generate AC electricity. So you try to convert that into DC and provide it to the electrolyzer to generate the green hydrogens. And majorly these kind of systems is best suited for offshore installations, wherein we can go on with higher cost savings, because establishing transmission lines through the seabed is quite expensive. So when you have offshore wind farms, you can go on with converting the energy that is being generated by installing an electrolyzer, a floating electrolyzer in the seabed, and generate hydrogen and store it, and you can bring it to the shores. So hybrid system is kind of utilizing both the solar as well as wind. And the main thing is both solar as well as the wind is kind of an intermittent energy source. So when you have a hybrid system, it tries to provide a consistent and uninterrupted energy supply, right? Because you have two complementary energy sources, solar as well as wind. So whenever you have higher solar energy and lower wind energy, solar will try to compensate the losses, right? So when you combine two or three systems, then thing is it can provide continuous production of green hydrogen as well. And as I said, CSP-based hydrogen production system, it can be used in the organic cycle, and it generates the electricity, and the electricity can be used for other purposes, as well as it can be used for electrolyzer to produce green hydrogen. And when we talk about wind and solar system, we require either AC to DC converter or DC to DC converter for managing the load adjustments. So the integration of batteries ensures uninterrupted operation, because the excess energy is stored in the batteries, and whenever you go down, you just substitute that, and it provides the continuous hydrogen generations, and it enhances the overall system efficiency. And hybrid systems can be categorized into on-grid as well as off-grid. So whatever you produce, you can give it to the grid, and you can utilize it whenever you have a lower production, or whatever is being produced, you utilize on your own. So the first one is about on-grid scenarios, wherein we have these wind, CSP, and solar PVs. So the energy that is being generated is used for charging your batteries, and it is also used for producing the hydrogen, green hydrogen, and the excess is being fed into your grid. So whenever you have, because this is a DC bus, so you need to have a DC AC converter to substitute to your grid. And whenever the production is less and you have utilized the batteries for green hydrogen generation and still you are lagging, then you can extract power from grid, and you can use it for the green hydrogen generation. So that's with on-grid. And off-grid is whatever we produce, we try to utilize that and store that in the battery and produce green hydrogen. So the difference major between these two is we decide what is the capacity of the hybrid system that we intend to develop, and what is the battery capacity that we need to have as a backup. So this has to be synchronized. If we have a grid, then whatever the excess that we produce can be given to the grid. But when you go with the standalone systems, we need to ensure proper designing of all these scenarios. So in addition to the green hydrogen generations, the electricity that is being produced can be used for different electrification process, heating process, cooling process, and desalination process. So one scenario is you generate the electricity with solar and use electrolyzer to generate the hydrogen. That hydrogen can be used back to produce electricity through fuel cell, and that can be fed into the requirements, right? So similarly, direct power from the solar will also be fed. In case you require more, that will also be fed through the produced green hydrogen. And this gives an overall picture of how the green hydrogen produces the required electricity and feedback to your systems. And the higher thermal energy that is being generated with concentrated solar power can also be used for thermal applications. Like you can use it for thermal storage systems and thermal electric cooling system. So there are a number of different scenarios how to incorporate these different kinds of hybrid systems for green hydrogen generation and also for other purposes. And I have just given a list of few here. And recent projects, I just categorize into three different scenarios: executed, under development, and approved. So executed, they have 100 megawatt solar PV for green hydrogen generations in Spain, and it generates green hydrogen at the rate of about 3,000 tons of green hydrogen per year. In China, they have a plant which uses 500 megawatt of solar energy, solar farm, and it produces green hydrogen at a rate of 3,000 tons per year. And under development is you have a NEOM green hydrogen project in Saudi Arabia, which goes for higher capacity of renewables. So roughly about 3.9 gigawatts of renewable energy they want to extract, and they want to utilize that for producing hydrogen and ammonia. And Oman also, they have targeted to go with 5 gigawatts of wind and solar capacity, and the green energy target is about 200,000 tons per year. And in India, we have two different projects that is being approved. One is with Dhirubhai Ambani Green Energy Giga Complex. So where they have identified space and in Jamnagar, and they want to produce nearly 3 million tons of green hydrogen. And the Indian target is about 5 million by 2030, and this is one of the major contributor. And Acme Group has started their work with generation of green ammonia. So about 213,000 tons of green ammonia they will generate in a year, and they have tried to have this plant in Tamil Nadu, Thuthukudi regions. So coming to the economic considerations, so the levelized cost of hydrogen production is influenced by different scenarios. That is the rated wind speed, the weather variables, what is the solar radiation that we intend to have, and the land availability, locations, and the type of electrolyzer used. And they have plotted graphs for different countries and different systems, right? So they go with solar PV, CSP, wind, and hybrid, and they intend to have cost minimum of at least $2, right? So this is the minimum cost that they can go for hydrogen generations. So when we come with technologies, the price range is somewhere about $7.5 for alkaline water electrolyzer. For PEM, it is 5.3 to 9.3. And for solid oxide, it's 6 to 9.34. And considering these scenarios, when you go with higher productions, obviously the cost involved will be reduced. So that's what India has planned, and it targets to achieve $1 per kg of hydrogen by 2030. So other emerging technologies for hydrogen productions, so direct air electrolysis. So it's kind of, when we talk about electrolysis, we need to have kind of fresh water, desalinated water. So what direct air electrolysis process is done is you have a hygroscopic electrolyte. So it's kind of a sponge material, and you allow the air to flow through this hygroscopic electrolyte material, so that the water vapor that is present in the ambient environment will be absorbed by this hygroscopic material, water attracting material, so that the water will be transported to the electrodes, and it generates the hydrogen, right? And the people go with even a low humidity level of 4%. They were able to extract hydrogen production from it as well. So this was recently came up in research article by an Australian university, right? And yeah, so that's a major thing. So you provide some physical barrier to remove the oxygen from the anode and hydrogen from your cathode. And next is membraneless electrolyzer, right? So always when we talk about electrolyzer, the membrane is one of the costliest parts. So, and it is also getting deteriorated, and the lifetime is also dependent on the membrane. So people came up with a device with the membraneless electrolyzer, wherein they separates the oxygen and hydrogen using fluid dynamics instead of a physical membrane, right? So when we eliminate the membrane, so the system becomes simple, and it's cost effective compared to traditional electrolyzer. And the fluid, it majorly relies on the fluid flow, forces on the fluid flow or the buoyancy to separate the products. So you have the electrolyte flowing directions. So this is the cathode and this is your anode. So when it gets in contact and it generates the ions and it generates your hydrogen. And at the outlet, you have some kind of product divider so that both divides and it is being extracted separately. And it offers low cost, efficient hydrogen production system, but it faces challenges with gas crossover. So 100% pure hydrogen can't be achieved with these scenarios, and research are under development for new designs to improve the performance and purity. And next one is with redox decoupling. So here they use a redox mediator to separate the oxygen and hydrogen evolution reaction in both space as well as time, unlike the conventional electrolysis. So the hydrogen evolution reaction takes place, splitting water into hydrogen gas, and the oxidized form of redox mediator is formed whenever the hydrogen evolution reaction takes place. So water gets splitted to form hydrogen gas, and you get oxidized form of redox mediator. And when the oxygen evolution reactions occur, so it is planned separately, right? So in that scenario, the oxidized redox mediator is reduced to produce oxygen gas. So these two things, you can keep on accumulating the oxidized form of redox mediator, and you can use it in some other place. You can transport it and produce oxygen in some other regions as well. And various redox mediators are being developed, including metal oxides, organic molecules, and vanadium-based compounds. And finally, the electrified steam methane reforming process, because as I said, steam methane reforming process is quite well established, and nearly 95% of the hydrogen produced is with steam methane reforming process. And the CO2 emissions from this is either you follow the water gas shift reactions and you generate the CO2 emissions. And for enabling the steam methane reforming process, it requires heat. So you need to provide heat at a temperature of about 700 to 900 degrees centigrade. And majorly this heat is provided by conventional combustion process in case of steam methane reforming process. Whereas with electrified, we use some kind of electric heaters to provide the required heat for steam methane reforming process, and by which means the conventional combustion process is eliminated. So whatever the CO2 emissions that is being emitted by this conventional combustion process is being reduced. So roughly it varies from 40 to 60% of the total emissions from the steam methane reforming process. And as you have an established setup, you can try to electrify the established setup so that you can reduce the CO2 emissions by 40 to 60%. So that's with the generation process. And next is with the application oriented things. I'll try to give a crux of these things within next 10 to 15 minutes. So we all know that hydrogen and ammonia is a green fuel because it doesn't provides any carbon emissions, and major emission that it comes out of hydrogen combustion system is only your water vapor. And if the temperature is too high, then the air, oxygen and nitrogen, the air combines to form nitrogen oxide emissions as well. So the fuel properties of both hydrogen and ammonia is favorable for engine operations, and but it has higher octane number. So it is majorly used in SI engines, and it has wider flammability, lower ignition energy requirement for hydrogen. So it can be operated in SI engine as such with stable combustion and better performance. But it requires some modification in the fuel storage and injection system because we are transiting from the liquid fuel to gaseous fuel. Right? So we need to have some kind of control system to avoid backfiring as well. So the volumetric energy density is too low, so which means you need to store hydrogen in terms of very high pressure systems, right? So Ashok Leyland and Cummins, they have come up with the design of storage tanks which can store hydrogen at a pressure of about 350 or 700 bar. So when you have 700 bar hydrogen tank in a vehicle, so it is equivalent to that of the gasoline fuel that is, or diesel fuel that is stored in that particular thing. So the major challenges with hydrogen is its safe storage, transportation, and handling. And it also, when exposed to metal, it will embrittle the metal. So ammonia is kind of considered as a hydrogen carrier, and it avoids the challenges associated with the hydrogen. But ammonia has, in contradiction to hydrogen, it has narrow flammability range and higher ignition energy requirement and lower flame speed, so which makes it difficult for ammonia engines. Ammonia, you have fuel bond nitrogen as well, so that nitrogen oxide formation will be higher. And also, ammonia is also toxic. So whenever you emit it to environment, it's also a major drawback, right? The property comparison of gasoline with hydrogen and ammonia, right? If you could see that the energy density, right? So compared to gasoline, energy density of hydrogen on mass basis is almost 3 times higher. But if you do it on volumetric basis, it's almost one by 10th of gasoline. So that's one of the major drawback with hydrogen. Right, I'll just skip few things. Right, yeah. When we talk about the fundamental characterization of this fuels, we intend to estimate the adiabatic flame temperatures, autoignition delay, and laminar flame speed. So hydrogen is highly reactive. So the delay in ignition is very small when it comes to hydrogen, whereas ammonia is a kind of a lazy or sluggish fuel. So the ignition delay is higher. And when it comes to flame speed, hydrogen is having higher flame speed and ammonia is very slow. And adiabatic temperature is also higher for hydrogen and it's lower for ammonia. And same with extinction strain rate. So whenever the flame expands and how it extinction during the when it approaches the end of the wall, how it extinguishes. That also is higher for hydrogen, whereas lower for ammonia. And hydrogen, it can be directly used in SI engines. You can use any one of these injection strategies. Either you go with carburetions, port or manifold injection, or direct injection. But compared to port and carburation technique, direct injection is advantageous when you go with hydrogen because it offers several benefits like improved fuel metering and improved combustion and increased power output, increased fuel efficiency. And the major thing is it avoids the risk of backfire. So whenever you inject hydrogen in the intake manifold, during the heat might get into the intake manifold and firing may happen in the intake manifold as well. So when you go with direct injection, these problems are avoided. But still, when you want to inject directly into the combustion chamber, you have to have high pressure gas injectors and high pressure storage tanks and high pressure distribution lines. So it kinds of complicate the things and it requires higher cost involved in these things. So these are the modifications that we intend to do when we go or adopt hydrogen for as a fuel for SI engines. Right, so 100% hydrogen usage may lead to pre-ignition, and thus we have to avoid going with stoichiometric mixtures, and we have to go with lean mode operation. You can see combustion curve here. So pre-ignition is before the spark, it will ignite on its own, right? So it once the pre-ignition starts, the combustion curve shifts. And in the 30-second cycle, it shifts it to a scenario where the combustion happens before the closure of the intake valve. So it's kind of very fast. And if the combustion happens before the closure of intake valve, then it backfires into your intake manifold as well. And the pre-ignition limit decreases and it also increases because of the cooling period. So it depends upon the injection time period, right? So it just decreases. And after that, it increases because thing is whenever you have late injection, so the mixing is deteriorated because you are injecting during the compression stroke and the mixing get deteriorated, because of which the pre-ignition limit again increases. And NOx emission is quite advantageous when it comes to hydrogen, that too lean mode of operation of hydrogens, right? So when you go with equivalence, lambda of 2.1 or more than 2, the NOx emission is way lower. So you can achieve nearly zero NOx with lean combustion as well. So some design considerations for hydrogen SI engines. So you have to adopt cold rated spark plugs because hydrogen is highly reactive. Even if you have hot surfaces on the spark plug, then it will auto ignite. So you need to have cold rated spark plugs, and you have to lower the spark plug gap so that the ignition voltage is reduced, and you have to avoid the residual ignition energy. So you need to have kind of proper grounding mechanism so that the residual ignition energy is not being used to ionize the gases in between. So it's kind of may result in uncontrolled combustion scenarios. And you can go for either timed port injection or direct injection so that there is no hydrogen concentration in the intake manifold and the backfiring doesn't happen. And we need to avoid the hot spots, either use additional coolant passage or you do proper scavenging and you align the air intake into the system in such a way that it takes away the heat in the earlier cycle and tries to cool down whenever the fresh charge is injected into the cylinders. And you have to reduce the piston top plant surface. And what happens is hydrogen is highly diffusive in nature, right? So when the hydrogen enters into your cylinder and when the inlet valve closes, it occupies the small gap between the wall and wall seat, and it might cause pre-ignition as well. So that has to be avoided, and proper sealing and proper wall seat design has to be done. And proper compatible lubrication oil is required because when we have hydrogen combustion, you have water particle that is being formed, and that should be accommodated by these lubrication oil. And you need to have positive crankcase ventilations. And here the compression ratio can be increased probably because hydrogen has an octane number of about 130. So compression ratio for SI engine can also be increased to a higher value of either 12 or 13 or more than that. And because of that, your thermal efficiency is dependent on the compression ratio. So it can be related as well. So increasing compression ratio will also increase your thermodynamic efficiency of your engines. And we need to reduce the in-cylinder turbulence because the flame travel is too fast, and if you have too much turbulence, it might extinguish the flame as well. I think it's almost time, so I think I'll stop here so that we'll have a 5 minutes discussion for. So these are all some of my works on advanced combustion system, wherein we use pre-chamber ignition systems. So we have a small pre-chamber like this, and we try to ignite the mixture here, and the flame travels into the engine, right? So that you can go for lower lean mixtures, and you can also achieve stable combustion. Whenever you go with lean mixtures, hydrogen, you reduce all the NOx, other emissions, and major problem is with ignition. So if you adopt these techniques, so you can achieve better combustion stability with lean mode of operation of hydrogen engine as well. So we are working on these things. And majorly, I work with combustion systems. And recent times, I have started using the hydrogen technologies like Turkish hydrogen generations, wherein we produce or we decompose methane to solid carbon and hydrogen generations, and which is of quite interest in recent times. So I started my research on that areas as well. And towards the final conclusion, so I just want to mention that the future is towards hydrogen energy for all major energy sectors. And looking towards the future, it's not only solar or wind that is to be utilized for generating hydrogens. It will also be of all the renewable energies that will be majorly used to generate hydrogen, right? So majorly, if we talk recent times, Indian government are keen on tapping the tidal energies, right? So tidal energy is one of the energy that is not being tapped by Indian government because developing these kind of systems in a harsh marine environment is quite expensive. But the tide energy that is available with us is too large. So the government has now recently initiated to go with extracting the tidal energy. And when you extract the tidal energy, one of the best way to store the tidal energy is by means of green hydrogen. And this is our nation missions towards hydrogen mission of achieving 5 million metric tons of green hydrogen by 2030 and majorly utilizing renewable energy for green hydrogen productions. So with that, I just wrap up my presentations. So we'll just open for a few queries, if any.
Good evening, sir.
Yeah.
This is Lakshmi Narasimhan. I am the Vice President of GRT Group of Institutions.
Yes.
First of all, thanks a lot for your excellent presentation and nice
Thank you,
opening of the opportunities for hydrogen for the future. I have a question. Actually, I have two questions. May I pose the first question?
Yes.
How about using hydrogen in case of this, hybrid electric vehicles? Okay, so how do we go about it? For example, coupling fuel cells with the conventionals. And what do you, as an expert, how do you foresee this combining, this hydrogen as a fuel cell, and then together with your hydrogen-based ignition systems? How do you foresee it?
The thing is, looking towards the automobile sector, hybrid vehicle is the future, right? So in next few years, whatever the vehicles that comes up with be with hybrid systems. And when we talk about hybrid system, you need to have a range extender. So either it goes with internal combustion engines powered by some renewable fuels, right? So renewable fuels is either low carbon fuels or zero carbon fuels and or fuel cells. And it's kind of evolving technology. And as for my knowledge is concerned, all the automobile manufacturers are investing on all technologies. For example, if you take Toyota, they are investing on hybrid, they are investing on fuel cell, and they are investing on hydrogen internal combustion engines and ammonia-based internal combustion engines. So looking towards the future, hydrogen or ammonia will take part either in the form of fuel cell or in the form of combustion engines, and it will assist the hybrid vehicles.
Very excellent, very excellent. If you allow, I can have my second question posted. Maybe
Sure,
I'm not
sir,
taking the
sure.
time of others.
Yeah.
Yeah, my second question would be localization of the standalone hydrogen-based power systems or electricity generation systems. So how do you foresee it, given the constraints like storage, the safety aspects, because it's kindly flames cannot be detected because of the colorless
Yes,
nature.
yes, yeah.
So how do you foresee that standalone systems or miniaturization?
So thing is, hydrogen transportation is like you're taking a hydrogen bomb along with you whenever you are traveling, right? So better is, as you mentioned, you have to have localized generations and use it whenever it's being required. And many industries are working on the safe transportation or safe handling of hydrogen. And it's still an area to be explored to utilize hydrogen in a large scale, sir. And that's what I can say as of now. And I'm also not very much expertise with this ideologies, but as per my knowledge, this is what I want to communicate.
Great, sir. Great session. Thanks a lot. Thanks a lot.
Thank you. Thank you.
Sir.
Yeah.
Sir, good evening, sir.
Good evening, sir.
Sir, can I ask one question, sir?
Yeah, yes, sir.
Yeah, sir, which one of the hydrogen production method providing higher efficiency, sir?
So efficiency is you ask about the electrolyzer techniques or
Yeah. Electrolysis technique one.
so electrolyzer, when we talk about the well-established setup, PM is the one which offers higher efficiency. And now people are coming up with anion exchange membrane electrolyzer. And the major purpose of this is it combines the low-cost elements, catalyst materials, and tries to mimic the same efficiency level as that of your PEM cells.
Okay, sir. Thank you so much.
Sir,
Yes, sir.
sir, can you suggest an area where a mechanical engineer can start research in green hydrogen?
Okay. So, kind of when we talk about green hydrogen, thing is people work on with this electrolyte and as I said, there are this redox material. So majorly, what I foresee is mechanical engineer. You can work on with the materials that is being used for this electrodes as well as the electrolytes, and find out some novel elements so that it can reduce the cost as well as provide better efficiency. So when it comes to green hydrogen generation, integration and generating power is uh, kind of well established and people are doing it. And the most required thing as of now is the materials, right? So it is better to concentrate on the material requirements, and we need to know some chemistry behind that as well. As now everything is interdisciplinary, we have to adapt to certain things as well.
Thank you, sir.
Participants, you have queries? Thank you, one and all. Good evening to one and all. On behalf of all, I am honored to deliver the vote of thanks for the today's session. I would like to express our sincere gratitude to Dr. Velraj sir from NIT Trichy for sharing his valuable knowledge and insight with us. His talk has helped us understand the importance of the renewable energy, hydrogen production, and also how hydrogen can play a major role in our future. Your express has truly illuminated the critical role in electrolytic hydrogen generation, sir. The session was very wonderful and effective and informative. Once again, I thank you, sir.
Thanks. Finally, I'd like to thank the organizer, Dileepan sir, and other people. Thanks for inviting, and it's a good session. Thanks.
Sir, thank you, sir. Sir,
Yeah,
thank you for your sharing.
Thanks,
Sharing your
sir. Thanks.
expertise with us, sir. It is a
Thank you
really
so much, sir.
informative and engaging section, sir.
Thanks
Thank you.
for the invite. Sir.
Thank you so much.
Thank you.
Thank you, sir. Dear participant, kindly wait for a few minutes. Session 3 feedback link posted in a chat box. Kindly utilize that.
Okay, sir.
ஓகே கேக்குது.
Ma'am, Shobana ma'am, good evening, ma'am. Can you start, ma'am?
Yeah, good evening, sir. I'm ready.
Okay. Once again, good evening to everyone. It's a pleasure to welcome you all today's session 4 on the critical forward-looking topic, smart grid and power electronics for hydrogen-based energy system. As we investigate the transition towards sustainable energy, integrating hydrogen into our power infrastructure, it is not just innovation, but a necessity. We are truly privileged to have the expert whose career beautifully bridges conventional thermal power on the frontier of environmental sustainability, a perspective vital for a parametric energy transition. It is with a great honor that I introduce our distinguished speaker for today, Mrs. R. Sobana. Mrs. R. Sobana is a senior engineer at the thermal power station, Mettur Thermal Power Station in Salem, Tamil Nadu, a key 600 megawatt facility operated by Tangenco. Currently, she serves in the Environment Management Division, where she plays a vital role. Her academic foundation is robust, holding a bachelor degree in the mechanical engineering from a Tandai Periyar Government Institute of Technology, Vellore, and master degree in thermal engineering from Bharathidasan Engineering College. Her professional journey is a testament to deep and hands-on expertise. She began her career on the front lines as a boiler operator at the very same plant and mastering the intricacies of thermal system. Over a past decade, she has challenged the operation knowledge into a crucial field of environmental management. Our work focuses on the pollution control, compliance, monitoring, and embedding sustainable practices within the thermal power sector. A background that grants a unique real-world lens on the challenges and opportunities of integrating new systems like hydrogen. Our experience from the boiler room to environmental stewardship makes our insights on the topic today exponentially valuable and grounded. Please join me in extending very warm and respectful welcome to Mrs. Sobana ma'am. Ma'am, kindly take over the session, ma'am.
Thank you, Mr. Dilip. I'm audible, sir?
Audible, madam.
Yeah, thank you. Hello, everyone. I'm Shobna from Metu Thermal Power Station, and I'm working as an environment engineer, as Dilipan sir said. Today, I'm going to interfere in the topic that smart grid and power electronics for hydrogen-based energy systems. Before entering into the topic, I'm very much grateful to Mr. Dilipan to give this opportunity to me, and I'm so glad to see all the dignitaries in this session. Who maximum everyone is doctorate, and I think I'm a little one comparing with you. So I will share my knowledge, what I have learned so much for prolong this 11 years. Actually, I had 11 years of experience in thermal stations. What are the challenges we are looking into there, and what type of issues we are facing due to the thermal thermal engineer thermal energy from thermal energy, why we need hydrogen based system, and how to maintain the grid. The grid stability of the grid is very much important, because being a boiler operator, I have seen so many grid disturbance during my tenure. What sort of disturbances? Just I need to explain my what I need to explain my practical difficulties, and I want to share my practical knowledge right now, because you guys are professors and you are all well versed with the theories and books and everything. Beyond that, what are the things I'm facing here is, it's a scenario that I am a boiler operator. I was a boiler operator since for 2 years or 2 more years, and we know about all the thermal process inside the boiler, what we have studied, and what here is there is entirely different, and the action, precaution, and prevention, everything is here. And being professors, you need to teach all the uh, what is that, a practical oriented teachings to all your students. It's my request. And coming to the point, why I am taking this topic is grid disturbance, because one evening, I was a boiler operator. The frequency maintained in the grid is 50 hertz. What is that? 50 hertz. At the time, suddenly the frequency of the grid dropped to 48 hertz. All the systems and everything got tripped immediately, one by one. One by one, it got tripped, and the backup source is not there. What are all the backup source? Base thermal load stations are the backup source. In Tamil Nadu, we have base load thermal stations in TNPGCL right now. It's previously, that is, it is called as Tangerco or TNEB. Now it is TNPGCL. It's our situation. That's exceptional. And now in TNPGCL, we have five base load thermal stations, and two numbers are in now is trial. The five stations are, as of you know, North Chennai Thermal Plant 1, North Chennai Thermal Plant 2. North Chennai Thermal Plant 1 is 3 into 210 megawatt, and North Chennai Thermal Plant 2 is 2 into 600 megawatt. And TTPS, that is Tuticorin Thermal Power Plant, which is 5 into 210 megawatt. And now here Metu Thermal Power Station is 4 into 210, and Metu Thermal Power Station 2 is 1 into 600 megawatt, where I'm working. So these are all the baseload thermal power stations. We can generate, what is it, from North Chennai, we can produce up to what is that, 660 megawatt plus 1200 megawatt from North Chennai. And from Metur, we can produce right of now 4 into 210, that is 840 megawatt plus 600 megawatt. And from Tuticorin, 5 into 210, that is 1050 megawatt. These are all the baseload power stations. If the problems, actually the problems may happen at any time. That is the scenario, because here we are having lot of equipments. For a simple gas or a simple what is that? We are using compressors, right? Here the compressors plays a very vital role in that. Even a simple instrument or compressor fails, the total power got shut down. Even that 600 megawatt, for a fraction of a second, the 600 megawatt vanished from the grid. So that the smart grid technology is very much essential to maintain the grid frequency. This is my point. That's why I have taken this topic. Even though I'm a mechanical engineer, why I go with this power electronics is, we are in that, not in that mechanical, electrical, electronics and all. we should know everything and the combined technology. In the power sectors, except in state government sectors, state government sectors are called as power engineers only. They have to know all the things. And now, so being power engineer, I'm facing lot many grid disturbances during my course of time. Later, when I quit from there, when I got transferred from boiler to environment, I have faced that entirely different things. What are the things are environment? Environment plays a key role in the thermal management because the issues in environment is lot. The first thing is handling of coal, handling of ash, that is the waste product which we got out of that coal burning. So the handling of ashes is critical and what is that unavoidable problem in thermal engineering, thermal power plant. You being a base load power plant, in the thermal power plant, handling of ash is very crucial. We have two types of ash. So one is dry ash and another one is wet ash. Normally nowadays we are using an indigenous coal from either from Indian coal or Orissa Talcher mines or Sinkarni mines, where whatever we received some Indian coal alone, it nearly have more than 30 to 40% of ash content. In 600 megawatt power plant, we need to produce the power. We need to generate 600 megawatt for a whole day. That is 14.4 million units. We need, being Indian coal, that is indigenous coal, we need it nearly 10,000 tons per day. So on the whole, we are generating nearly 4,000 tons of ash in a day. In that, we have 80% of fly ash and 20% of bottom ash. Here, the peculiar technique we doesn't have a wet ash techniques. Only we have dry form of ash to dispose the things. In that, 85% is collected from ESP. As all you know about the thermal power plant. So I believe that ESP, you may know, aware of that. Through ESP, the fly ash collected to silos and disposed to somewhere. Some of cement industries, brick manufacturing units, like that. Many of the things taken away the ash, and the bottom ash, which is a coarse one. The bottom ash, which is a coarse one, that has that should be used in the crusher. One just a minute. So before entering into my topic, I'm saying all these things. So why I'm taking this? That's why I'm explaining everything. Bottom ash is a coarse one that we can use in the M sand, like other things, or crushers to be handled and mixed with that cement. So not only going with ash and also handling of coal, the fugitive emissions from coal, the emissions from the pulverizers, and the reject coal. What is that? What is the reject coal is uncrushed coal, which evacuated out of from the pulverizer. That handling of so many issues in environment. So all these things we are facing day to day life, and I'm dealing with all the pollution board correspondence things. So pollution board in the sense Tamil Nadu Pollution Control Board and Central Pollution Control Board, and we are dealing all the MOEF, that is Ministry of Environment, Forest and Climatic Changes notification and all. Consistently, the MOEF, CC and CPCB and the CA, TNPCB, every government body releases the notification then and there and giving the guidelines on how to handle everything. So all these things are coming routine in our environment management cell in thermal, and not only in thermal, being gas turbine power stations and all other things. We day to day life, we are facing so many environmental impact. If somebody visits to that North Chennai area or Mettur or Thoothukudi, you really face the problems. What are the problems we are facing? You can see directly, because the evacuation of ash is too high, and the quantum of ash deposited in the dike area is too high. So these are all the base reasons. That's why I'm taking this subject, that is green hydrogen. The green hydrogen, the previous session I have seen the sir explained all the things how to produce green hydrogen, and now I am dealing how to store green hydrogen and how to use in the smart grid. Smart grid in the sense, just like the UPS. Whenever the power switches, power cut in our home, the inverter starts and it releases the energy, that is electrical energy. Then we done our routine life. That's the same thing I'm going to explain right now. And like before that, I'm saying entering into my topic, and not only facing day-to-day problems due because of ash, and also facing so many emission factors, that is SO2, that is sulfur dioxide, nitrogen oxides, and carbon emissions, everything, carbon monoxide emission from coal. We are all facing all these things, and these are all affecting our atmosphere, and it leads to global warming, and subsequent and consequent causes may arise. So now I'm going to enter in my topic. So demand, that is what is that? So far I have spoke about that clean energy, that is called clean energy and sustainable energy, that leads to the hydrogen based energy systems. That is the hydrogen H2, which is easily available, and it doesn't harms our environment and doesn't harms our health. So H2 based energy systems with modern electrical grids, because nowadays modernized terms are very important in our life, and that is smart grids equipped with advanced communication, automation, control technologies, which plays a crucial role. That is the thing. Smart grid, what I have explained already, the grid frequency should be maintained at 50 hertz. Whenever the surge or any problems may arise, that should be refilled, that should be backed up immediately with the alternate power source. For example, if the power gets shut, if the plant tripped, unfortunately the plant gets tripped, the 600 megawatt got dumped. The backup source for the 600 megawatt can't be maintained by the grid. The grid engineers may struggle a lot. That name called load dispatch center, that is LDC engineers. So they have to maintain the grid. They have to source the power, and they have to always have a key plan with them. So instead of that, the stored energy from somewhere, like our battery or like our fuel cells from H2, that instantly that 600 megawatt can be refilled immediately. That technique may help the people and may avoid some surge attacks, everything in the grid. So that's why smart grid is the optimum technology to play the crucial role and in efficiently managing the production, storage, and utilization of hydrogen energy. So power electronics acts as an interface between renewable power sources. So why power electronics? Because it has so many devices, and it is the only way to use the stored energy where and whenever we need. That's why the power electronics plays a key role. Actually, we named this as digital twins, like digital twins in the same power electronics smart grid combined with hydrogen energy that will give zero carbon, zero emission fuel. So the between renewable sources, electrolyzers, hydrogen storage units, and fuel cells, enabling efficient conversion and control of energy flow. So, and likewise, I told the energy from thermal power plant leads so many CO2 emissions, so much of CO2 carbon emissions, not only CO2, NOx, SOx, everything. Even MOEFCC gave the guidelines to maintain the SOx and NOx within limit. Like we thermal power plant more than 500 megawatt, we have to maintain 50 milligram. That is a normal metric cube per normal Newton per meter cube. That is Nm per mg cube. That is 50. SPM should be in 50. SO2 that should be in 200 milligram per Nm cube, and NOx should be in 450 milligram per Nm cube. These are all the limits. This should be in the where it is outlet of the flue gas. So for that we need so many so many devices, technologies to maintain these limits. To avoid these many technologies, we can go with that green energy systems like the hydrogen, green hydrogen, as sir told, green ammonia systems is very effective. Actually, the smart grid and power electronic technologies together enhance that flexibility, reliability, efficiency of hydrogen energy system by enabling real-time monitoring and bidirectional power flow. This is the main thing, that is bidirectional power flow. Whatever, whenever the power source supply, we can store the power. Whenever the power is not there, we can release the power. That is bidirectional power flow is so important. What are the, which is a technique we already used in hydro stations, as we can use that as the water from downstream to upper stream to convert to act generator, and the upper stream to downstream to act as a pump. These things are already using, and grid stability and support and demand side management. Demand side management is the exclusively term because we are facing a lot many issues in demand side management. Demand side management should not be in a consistent way. It may rise, it may get lower, it may build it. It depends on the season, it depends on the monsoon, everything is there. So demand side management is the crucial thing. That's the smart grid is the only thing that can easily come over the term. This integration supports large scale renewable energy penetration. So the renewable energy penetration is, I'll just say a simple example with that. Being thermal plant in morning, in summer, in one summer morning, you can imagine, in morning we get solar energy for about 600 megawatt nearly. For instance, we can get solar energy. By the day, suddenly the cloud movement, everything has happened, that suddenly get dropped. So what we need to do here, immediately set up, we need
Ma'am,
to
excuse me,
attach.
ma'am.
Yeah.
Sorry for interruption.
Yeah.
Kindly share slide in PPT slideshow, madam. Switch on the
Slide.
switch on the slideshow.
Okay. I'm doing, I think.
In PPT.
One second, sir. I think I'm in that, sir.
In bottom, in the Zoom, and 69% is there. Or top in animation, insert design animation slideshow.
Layout and note, slide control. Okay. Is there, sir?
Resume slideshow.
I'm in resume. Okay. So actually, I'm in that. I'm audible, sir?
Ma'am,
Sir?
audible, ma'am. Audible, ma'am.
Yeah, thank you. Sorry for the interference, sir. Sorry. I hope everybody had your supper. Okay. So, actually, I think I have stopped in that renewable energy penetration with solar. So, during the peak summer generation, if we can able to store that solar energy as an electrical energy, that should be a main backup source for the grid disturbance while during the grid disturbance. That's why it is the main thing on focusing this smart grid technology, and it also helps in achieving low carbon and sustainable future power systems. The sustainable is the word which is a greater thing, and the sustainability is main thing for our future generation. There is a low carbon. Actually, we should say like zero carbon. Zero carbon can only save our future and future generation also. And here is the small block diagram. Actually, that is the thing from renewable energy. The renewable energy we can produce from electricity from solar, wind, tidal, hydro, and everything. Except non-renewable, except from non-renewable sources like gas turbine stations or thermal stations, everything is renewable energy sources. So that renewable energy may stored as may be used in that electrolyzer. The electrolyzer can split hydrogen and oxygen, and the hydrogen can stored in the storage container as many forms. That is one thing is liquid hydrogen, and there's metal hydrides, and another form of in high pressure tanks we can store. And later that hydrogen, the stored hydrogen can be used in the fuel cells, and that fuel cells can generate electricity, and that can be supplied to the electric grid whenever and wherever required. So this is the small block diagram what in my mind that I have shown here. And the fuel storage, as of now we know that a battery can store electrical energy, and also like that fuel cells can also, sorry, hydrogen storage electrolyzers are also used as hydrogen, and hydrogen can use in fuel cell to regain the electricity. That is the hydrogen versus battery storage I'm showing here. That is the batteries is for fast short-term response, and hydrogen for duration, seasonal, and energy shifting. The storage duration, comparing with the battery, the hydrogen can store in months, and energy density, the hydrogen is have more. And efficiency is also comparatively, batteries are in -90, and hydrogen is -35. And coming to our point, that is smart grid. A smart grid, that is the distribution system that develop a power grid more efficient and reliable, improving safety and quality of supply in accordance with requirements of digital age. That is called digital age. Even now we are using the grid technology, and so many updations in smart grid technologies. Before we have the grid only in southern region, northern region, western and eastern. Now it is a centralized grid wherever the power generated in Orissa or power generated in Uttar Pradesh can be used in Tamil Nadu or Kerala, everything, because smart grid can combine all the generating stations in one under one umbrella and supplying the power throughout the India. And I think something happening. Okay, with requirements.
Wait, ma'am, few minutes. Ma'am, you continue, ma'am. I will make arrangement.
Okay, sure. No issue, sir. I can change the slide. So smart grid can use of renewable sources as or distributed generation. Higher penetration of renewable sources, sir. Actually, the motto is we have to go with low carbon food, zero carbon, and what is that to say? Green energy. Green energy is our ultimate motto. To utilize that green energy, we need to switch over that smart grid technology. May use and we can use more over that and extending an effective communication overlay from generation to the consumers. This is the exact point. Nowadays, we are using some solar meters, solar things that we can store, we can give the energy from our solar panel to the grid, and night we can draw. That's the plan. Previously, government has imposed in distribution side like that. That effective communication overlay from generation to the consumers and use of advanced sensors and high speed control. These are the basic requirements to arrange with smart grid, which gives a higher operating efficiency and greater resiliency against attacks and natural disasters. Automated metering and rapid power restoration. This is the basic thing. Automated metering is the need and the utmost thing right now. And product greater customer participation, and the customers may know about how much we can generate and how much we can use. This knowledge is very much essential to use the proper way of electricity, because we power engineers know from for your information I'm saying we generate 600 megawatt, okay, but due to the conversion line losses and the customers side losses, the customers can reach the power can reach up to the customer that is only 300 megawatt. If we generate 1 megawatt, the customer side can reach can able to reach that is 0.5 megawatt only. Balance 0.5 megawatt is what is that? They are that the things are went losses. So use of electricity is the most awareness thing to be known by the customer or the people. Being people, we should know how to use electricity. This is my point, because for generating one unit, we use more than 1 kg of coal. The 1 kg of coal emits more than 400 grams of carbon emissions. Likewise, you can calculate. In smart grid versus electrical grid with communication. Why smart grid? That's why I'm showing this. So Indian electricity system already facing that n number of challenges that which can overcome by smart grid. That is shortage of power theft, and poor access electricity in rural areas, and huge losses in the grid. As I said already, the line losses is the major thing in here, because we are generating the power. The transmission losses is too high. Roughly, the half of the power we generate is can able to reach the people, and poor reliability. These are all the things can overcome by using that smart grid. This is just a layout diagram. So generation, transmission, distribution, and power consumers. These are all the different companies. The one and one is not linked right now because KNEB get distributed, and now generation is apart, transmission, distribution is apart, like this. So here we are generating the power from biomass, nuclear, thermal, hydro, wind, and solar. And the transmission centers, that is the big lines, are we all aware about that. And the distributing stations, that is power stations, that from where we have so many stations in regional areas and everything. From there, the consumers can receive. Actually, the concept of smart grid is where the power required, and like that. If we need power, we can avail. If we don't need, if we doesn't need, we cannot. That's the thing we need to know about smart grid. And coming to the point, that is hydro energy. So hydrogen energy. That is hydrogen energy is a clean energy. That is which has zero carbon emission. When you use in fuel cells, this is the what is that nowadays seeing all these things, the hydrogen can be the most adequate thing to overcome the zero carbon, as already we are facing ozone depletion, global warming, and most of the climatic changes are all we are facing. So we need to change over all these things. So we have to go with hydrogen. hydrogen as a clean energy, and it supports the decarbonization across power, industry, and mobility sectors. It's of really the mobility sectors. I'm not that much aware about that, but in power sectors, the emission of carbon is too high. We are doing so many things to reduce, and we need to buy some carbon credits and carbon form of certifications. Everything is there, but the decarbonization process is the utmost thing when we use this hydrogen energy. And hydrogen energy, not like batteries, we can store for a month, can be stored for a long time. And also hydrogen energy is easy. I think it is to produce 1 kg of hydrogen, we need 33 point up to 23 to 33 units of electricity is required. That is for we need to apply in electrolyzer, and we need to split the hydrogen, and we need to store that. So 1 kg production of 1 kg needs 33 units of electricity. And the main components of production in hydrogen energy, as you all know about the previous session, sir have explained all the things clearly. The thing is electrolyzer. The energy from renewable sources has been directly introduced into the electrolyzer. The electrolyzer have that what is that? The electrolyzers can split the hydrogen and oxygen in different ways. Hydrogen can be stored in the cryogenic process or by pipelines to directly utilization or metal hydrates. And oxygen, the released oxygen can be used in some other way in medical and medical industries, and some other way in industrial process for other things like welding process, etc. So there is no wastage in the production of hydrogen. That's why hydrogen is the clean energy. And now we are speaking about green hydrogen, because green hydrogen is stored from the renewable energy sources. It's like that. I have come over the terms that gray hydrogen and blue hydrogen also. So for the information, I'm saying that is gray hydrogen and blue hydrogen are also available in that. And hydrogen storage technique is compressed gas or liquid hydrogen or metal hydrates. Now, actually, here we have separate hydrogen gas making plant for our generator cooling also. For the information, I'm saying hydrogen is not easy to handle. But we need such more SOPs to handle that hydrogen, and the government of India is working on that to how to protect and how to handle safely the hydrogen, and how to transport and everything. Actually, the mission of our Indian government is to generate 5 million metric tons by 2030, and by 2070 we need to go up completely by zero carbon fuel, and replacement of fossil fuels and self-reliant economy is our motto of our Indian government. By 2070 we shall be using green hydrogen energy only. These are all the informations I have received. This is a hydrogen energy flow diagram, that are renewable energy that converts electricity, that are converts hydrogen to electricity, renewable energy to electrolyzer. What we have already told, that electrolyzer acts the splits that H2 and O2, acting electricity as a catalyst. The H2 and the O2 got splitted up, and the hydrogen is stored in this tank. This is just I'm showing this simple example. And again, this hydrogen is giving input for the fuel cell. In that fuel cell, the hydrogen reacts with that cathode, and it produces electricity, and that electricity is used by the grid. Between that production of electricity and the grid, the so many processes are taken over by the power electronics department, and that's the need to do all the voltage fluctuations and the grid maintenance. Everything should be done by the power electronics, and that will be come over. And that is types of fuel cells may be types of hydrogen making technologies, that is PEMFC, that is proton exchange membrane fuel cell, and a solid oxide electrolyzer fuel cell, like that all. And hydrogen transportation and distribution is just the on-site storage is like in cylinders, and for the immediate purpose we can transport through pipelines, and for the prolonged purpose we can use that in the truck or compressed cylinders. And some more, one of the other techniques is underground storage technology is also available in that hydrogen transportation storage techniques also. And power electronic interface is here is DC-DC converters, AC-DC converters, inverters, bidirectional converters. As already I told that bidirectional converters plays an important role. So this is a power diagram that is two-part solution. When these two things combine together, and we can achieve so many good things to protect for our sustainable life and the thing. The smart grid. The smart grid is that an intelligent bidirectional electricity network. It provides the digital communication, monitoring, and control layer needed to manage complex distributed energy resources. the, the smart grid. The smart grid is nothing but just imagine just our mobile phone. How mobile phone takes our life that much easy, like that only. And here that hydrogen-based energy system, which is longer duration chemical energy storage medium, it's the vessel we can use store massive amounts of surplus renewable energy for weeks and months, solving intermittency problems. Intermittency problems that we know for light up, that is we need to uh, bring back the power plant. Once it gets tripped, we need to bring back the power plant. We need minimum of, for our plant we have two startups, that is one is hot startup, one another one is cold startup. In hot startup we can bring back the power plant within 8 to 9 hours. For the meantime, what we will do, we can go with either purchase from the private parties or from the renewable sources. Instead of the, if we stored our energy as in the form of hydrogen, we can use our own energy, so that the what is that, the financial benefits are more in that. So that is that called the surplus renewable weeks per month, solving intermittency problem. For a coal startup, it nearly takes 36 hours to bring the 600 megawatt to grid. That's why that the stored energy can bring give the backup source to the grid. If you think that is black startup, the one thing happened that black startup, that is called if all the grid has the power, if whole grid gets blocked, there is no power at all. How we start we need ignition, right? That is called we need the if you give electricity, then we can produce electricity. For that, here we use matrix boilers with that LPG cylinders and all. If we have this hydrogen based fuel storage system and we can generate electricity from there, then that matters also easily. We can avoid block startup also. So this diagram that shows that a complete energy flow, that is renewables from solar to the smart grid. So generation sources, and here we can store in both the ways, one thing as battery, another thing as fuel cell. And here I'm showing that for an example, here it is EV station. So these are whenever, wherever required, that is the main motto in that smart grid. The central power electronic interface acts as a gateway, managing the flow of energy to the hydrogen system and from the hydrogen system back to the grid when needed. So using excess power in the grid, we can generate, we can store hydrogen. Whenever the power required, we can release hydrogen as electricity. This is called two-way energy. And here, coming to the point, it is a power electronics. Actually, if the power electronics plays a key role, even we are generating all the things, but without the electronics and the modules and everything, we can't generate electricity, or we can't store, we can't transport and transmit everything. So the power electronics is the field which combines electric power, electronics and control systems. The power engineering deals with static and rotating power equipment for the generation, transmission and distribution of electric power. Yes, exactly the power engineering deals. That's why we in NTPC and some of the central government organizations, everybody named us as power engineers, not as mechanical engineer or civil electrical engineer. They are naming us power engineers only. And the electronics deals with all the semiconductor power devices and power conversion to meet the desired control objectives. And control deals with static and dynamic characteristics of closed loop system. And the power electronics may be defined as the subject of application or solid state power semiconductor devices. The thyristors or plays a major role, and IG based rectifiers also the major role in this smart grid technology. And you or all may know very well about that thyristors and all the terms. So here this simple integrated technique of how I'm giving that small microgrid technology, and it is from see we have wind generators, PV modules, micro turbines, fuel cells, and here the power electronic interface connection, and here the power electronic interface from grid. The microgrid which stores the fuel cells and which releases the power when and wherever required, and the interfaces or everything comes under this thing. So in the applications of these power electronic contents are many places. The thing is commercial. First thing is commercial application. Heating systems, ventilating, air conditioners, central refrigeration, and lighting. So everything we need, whatever, whenever, and the domestic appliances. And I have given a lot more things here. And we can use this power electronic technology to face to overcome all the problems and all. And now, so grid to H2, that is uh, grid to H2, which shows that from our grid, and the challenge is to convert high voltage grid AC power, the electrolyzer interface technique, that is massive, stable high current DC power that electrolyzers. It's not a full like a phone charger. It takes so many AC/DC converters and inverters. Everything is required. And thyristor based rectifiers and IGBT, that is the insulated gate bipolar transistors rectifiers, is using here. The thyristor based technology, these are 12 pulse or 24 pulse diode thyristor rectifier. So the workhorse solution, and the process robust, reliable, high power. We can use this thyristor based technology to the smart grid to maintain the voltage stability and voltage to avoid the voltage fluctuation and all. And it is low cost. The cons are poor power factor, injects significant harmonic distortion, and has one-way power flow only. But here the IGBT techniques, that active front end, that is PWM rectifies, it is saying that smart solution, and utility power factor, low harmonics, higher efficiency, which is a bi-directional. We can send power to the grid and we can take the grid power from the grid also. But this is in the higher cost. That H2 grid, that is hydrogen to grid, that is fuel cell interface. Here, hydrogen storage tank to grid, how it is interfacing is using like. The challenge here is the opposite. A fuel cell produces low variable DC voltage that changes with the load. The grid needs AC-DC converter and this DC-AC converter then to the AC grid. So H2 grid is for utilization. So here that some DC-DC boost converter and DC-AC grid tied inverter. So the DC-DC boost converter creates that for safety and efficient high voltage buses can be handled with DC-DC boost, and DC-AC we can use IGBT switches and three-phase for exactly sync with the grid. DC-AC grid tied inverter is the good one to do. And here I give some of the techniques and control to the how to handle with that. And so this is a duck curve, that is here it is showing that in high solar noon, and demand in that evening, because in the daytime we do not use that much of electricity for lighting or for household utilities or else. Only the commercial peak load time is 6 to 9, and evening 6 to 9 is the peak load time. So at the time the electricity need demand is very high. That shows the ductneck curve. So here grid to hydrogen. So G2H shows that during duck's belly noon solar cheap over, the P acts as rectifier, that is observed. Whenever the demand is less, if we have surplus power in the grid, we can observe that power from that grid and produce hydrogen. And later, whenever the demand is high, it acts as inverter, that grid, the H2 can release energy to the grid, that is electrical energy to grid. That for all these things, the power electronic plays an important role. And these are all the inverter as the personality, that is grid following and grid forming. The grid following, the inverter listens to the grid with a PLL and injects the current. It's a follower, this standard but requires strong stable grid function. And grid forming, that is the inverter leads, it ignores grids and creates its own voltage and frequency, and synthetic inertia will create, and this essential for 100% renewable grid, because we can use power from renewable source, and whenever it is excess we can draw from the grid. So here the advantages shows that enables large scale integration of renewable energy, provides efficient hydrogen production, storage and utilization, and improves grid reliability, resilience and power quality, supports bidirectional power flow and real-time energy management. And its main important thing is it reduces the carbon emission and enhances energy sustainability. Power electronics ensures smooth voltage, frequency, and power flow control. So whatever we generate, but we need 220 volt AC. That is the main thing. So that's why we have to do all the integrations with this smart grid and renewable energy sources. The sustainability zero carbon will be enabled very soon, and it's the smart monitoring and demand response and cost optimization. The main thing is cost optimization. To generate 1 unit of electricity from thermal station, based on the performance of the thermal station, it may varies from 5 rupees to 10 rupees. But for domestic purpose, government is giving for up to 100 units, they are giving free of cost, and for after that they are charging. But here the generation cost is too high. If we use the available renewable sources, and if we store all the energy from here, then the cost optimization technique plays a key role in that. What is that? Storing of hydrogen, using hydrogen in the smart grid technology by using of power grids, power electronics. So why I'm repeatedly saying that cost optimization is the maintenance and maintaining the equipments in the power stations is so high, and the daily maintenance cost, it's also high. It's directly implemented in the generation cost. That is called, one is fixed and one other one is variable cost. Even the coal transportation from various sites, from rails to plant, then from offshore to onshore, everything is there. So we need to optimize everything. So we must go to renewable sources is the main thing to avoid lot more problems in future. So challenges is high initial and investment cost. Exactly, it is high initial and investment cost, because even in the government projects have started right now only for about another 5 years. We can most aware about that. Probably now 2 to 4 gigawatt per annum has been generated by so many concerns in India itself. And in Japan, it shows more technologies in production of green hydrogen and the usage in green hydrogen. And complexity in system integration and interoperability, efficiency losses in conversion process. Every process have loss. Without loss, there is no good thing will come over. So electricity to H2, H2 to electricity. Whenever the process starts, we may know, came to aware about that the losses, what are the things. From my point of view, water, that is a generation of H2O, that is a byproduct when H2 is converted to electricity. But it's not that much problem when we use municipal wastewater. From that we can use we can generate H2. Again, that water may be used for some other purpose, being water. Something for a control strategy and to maintain grid stability. The last before the point, hydrogen storage, leak and safety issues. Before that, one of the person asked that question that H2 is like a bomb, how we handle. It's like a bomb, but there is lot more of SOPs are there, that safe operating procedures are there. If we use in this positive and the proper way, we can use all these things in that way. And right now it has limited standards and regulatory framework, but in future, I think we may get much more things. By 2070, as our India government says, it is our motto to bring back green energy challenges. So I hope that that green energy will come back and it will give sustainable development for our society. Being thermal engineer here, I'm practicing environment management techniques in my own way. I request all our dignitaries to practice much more benefited and green practices. That's something like we use 3R, reduce, recycle, and what is that? Reuse, reduce, recycle, everything that way. You may all know about all the environment management techniques and all. And as of now, we have facing the challenges, so many challenges in generating electricity. The first thing is load stability, that is grid stability. Whenever requires, we need to give power. Whenever the power not required, we have to reduce. What will happen? The exact surge will happen, that is thermal surge. Thermal surge impact immediately. We need to go for 540 degrees Celsius with steam temperature with for 17.5 megapascal. If the grid shows we doesn't need power, you have to reduce the power to 300 megawatt. We need to reduce immediately. What will happen? The life cycle, what is that? The performance of the machineries gets reduced day by day, and it may get deteriorated. And we are facing so many issues and everything. For the example, we are facing issues in air preheaters. We are facing issues in the dry con distributors, and even in turbine, even in the hydraulic systems, and everything day by day. Even in the cooling water pumpers, even loaded acid loading, everything. Not a simple thing is not. It is not easy to generate power. That's why I'm repeatedly saying that if it is a way to go for green energy, we can go with green energy. It is, I think so. I have covered the techniques and what I have learned, and I have shared my own experience here. From here, I'm wind upping the session, and here it's my sort of gratitude towards the institute who called me here, and thank you, sir. I think, is there any queries? It's not.
Participants, if you have any queries.
Actually, the topic is related with environment. That's why there is no queries.
Okay, ma'am.
Okay.
Sir, HOD sir, can you close?
Yes, madam. Thank you, madam.
Yeah,
Given,
thank you so much,
sir.
sir.
Sir, can you
General
close?
good. Yeah.
Ma'am, thank you for an excellent and insightful session, ma'am.
I may think that I am not that much interactive because the given topic is I think I am the suitable person. I thought so. If I am vague, I'm sorry. Okay.
No,
If
ma'am.
you
No,
get if you get some
very
more
useful
things,
to us.
if you want to know about what are the aspects we are doing in thermal stations, I'm ready to explain everything. And now we are facing the challenges in the environment. That's the main thing I want to share with everyone, and that I have conveyed. I thought so. And thank you so much to the
Thank you,
GRT
ma'am.
institution, and thank you, Mr. Dileepan, to call upon me to hear. Thank you.
Thank you, ma'am.
Mhm.
Ma'am, I'm delightful to say our sincere thanks to Mrs. R. Shobana, ma'am, for your exceptional presentation today on a smart grid and power electronics for hydrogen-based energy system. Your deep expertise drawn from a decade of hands-on experience in both operations and environment management at the Mettur thermal power station gave us truly grounded and practical perspective. You have not only illuminated the technical pathways, but also highlighted the real-world possibilities of integrating hydrogen into our energy in future. Thank you for sharing your valuable time and knowledge and insight with us so generously. Thank you, ma'am. This officially, thank you to ma'am.
Thank
you,
you,
ma'am.
Mr. Dileepan. Please save our environment, use less electricity, please educate your children. Because I'm in the place, that's why I'm repeatedly saying why this girl is saying like that. You don't believe me. Here, the production is very tedious nowadays. Think upon that. You save electricity. Thank you.
Thank you, ma'am.
Mhm.
This session officially brings to today's session to close. We are excited to continue the journey tomorrow. This session will begin tomorrow at 6 p.m. Thank you all once again, participants. Kindly fill the feedback form find in your chat box.